Hello. So we are going to talk about the titration of a weak acid with a strong base and possible calculations that you might need to do related to that. So I'm just going to focus on 3 of the calculations you might need to do. One would be to calculate the initial pH of your pure weak acid solution. The second would be to calculate the pH here in what we call the buffer zone. This is before you reach equivalence. And as we've learned now, before equivalence we have both HA and A- present, and so that actually makes it a buffer in this zone, which is why the pH isn't changing very rapidly. And then at equivalence you are left with pure weak base left behind. You're left with the conjugate base. So first step, if you're trying to find the pH at 0.1 here, it is just a straight ice chart for a weak acid. So you would write out whatever your acid dissociation is. So HA makes H plus A minus. You can write out a Ka expression for that. Ka is H plus times A minus over HA. And you will be given a Ka value. Like for example, let's say we're using HF, hydrofluoric acid, you'd be given a Ka value for it. If we were titrating 0.1 molar HF, then I would plug in here under my initial concentration of acid 0.1. I'm going to say I'm starting with 0 of these. Some of my acid is going to get used up and it will be turned into these products, 0.1 minus X, X, and X. Notice how these are in a 1-to-1 ratio, so you don't have to worry about coefficients in the change column when you're doing these acid-base ones. If you go through and plug this into your K expression, typically the value of K will be very small, so we can assume that 0.1 minus X is essentially just going to be 0.1. So usually this concentration remains the same in equilibrium. We can ignore this change, it'll be insignificant. So plugging into your K expression, you end up with X squared over 0.1 equals whatever your Ka value is, which would be given. And then you can rearrange, solve for X. Notice X gives you your H plus concentration, so that means that the log of X would give you your pH. The second scenario, this is the trickier one, is when you are before equivalence. So you need to think about these as a 2-step problem. First step is a moles problem, where you figure out how many moles of acid did I have, how many moles of base did I have, what's left over and in what amounts. And then you convert those into molarities and you can use an ice chart. So again, first step moles, second step ice chart. If we want to use some numerical example, let's say I've got 100 mils of 0.1 molar HF. That means that I've got 0.1 liters times 0.1 molarity means I have 0.01 moles of my acid. Okay? I'm going to do the same thing with my base. I've got 0.08 liters times 0.1 molar. I've got 0.008 moles of my base. Notice how I have less base than acid. So that means at this point, after these react, I'm still going to have some excess HA left over. And that makes sense because I'm not at the equivalence point yet. So I haven't reacted all of my acid. So what happens, all of my base will get used up, so all 0.08 moles of it will get used up. And then every OH that gets used up will react 1 mole of HA. So if I start with 0.01 moles of HA, 0.008 of them will be used up, so I'm left behind with 0.002 moles of HA. It's also important to realize that for every HA that gets used up, each HA will turn into an A minus. So if this is our change column, my amount of A minus will go up by 0.008. So after this reaction is over, I will have no hydroxide left unreacted. That gets used up. I'll have 0.002 moles of HA left over, and I will have made 0.008 moles of A minus. So now I find that I have a solution containing both HA and A minus. And there's actually 2 ways that we can solve this. So one way is using an ice chart. So we can go through and say, I, C, E, and plug in your concentrations of HA and A minus that you have at this point. Keep in mind, these are in moles. You want these to be in molarity. So 0.002 moles divided by my volume, which is 180 milliliters. So that would be 0.002 moles divided by 0.18 liters. That would give me my concentration. I'm going to assume this starts at 0. Technically it doesn't, but the assumption works out well. My A minus is 0.008 moles. And again, that was in, at this point we have 180 milliliters because we started with 100 mils, added 80 mils to it. So make sure you pay attention to what your volume is as you go. So you can do it this way and solve for x just like you did over here. It's the same expression, it's the same Ka value, so you can solve it that way. We've also learned at this point this equation called the Henderson-Hasselbalch Equation, so feel free to use that as well whenever you have HA and A minus present. So that would be pH equals pKa plus log of A over HA. Hopefully I got those in the right order there. So look on your equation sheet. You could do either one of these methods for finding the pH at this point. The last step, when you're finding the pH at equivalence, keep in mind here you are left with entirely A minus. Okay? So what is happening is the A minus is a weak base. So it is going to react with water, take a hydrogen from water, because bases are hydrogen takers, acids are hydrogen givers. It is going to take a hydrogen from water, leaving behind HA and OH minus. So you can set up an ice chart. When you do that, a couple of key points to keep in mind. One is you are dealing with the conjugate base now. So rather than using a Ka value, you should be using a Kb value. If the Kb value is not given, look on your equation sheet and you will notice that the Ka for an acid times the Kb for its conjugate base. It only works if those two things are conjugate acid-base pairs. When you multiply them together, you will get Kw. The value of Kw is also given. That is 10 to the negative 14th. So that's for the dissociation of water. That's where our 0 to 14 pH scale comes from. So if you are given Ka, you can figure out Kb using this relationship. Other things to watch out for, notice that in this case, if you use an ice chart, when you solve for x, you are actually solving for the hydroxide concentration. So if you take the log of x, you will be getting the pOH. To find the pH, remember pOH plus pH equals 14. So don't forget to do that step. The other thing to pay attention to is to keep in mind that your volume, again, has changed. So at equivalence, you need to figure out how many moles of my weak base do I have at that point. Just like I did down here, you'll figure out moles of your weak base. And it should be that all of my weak acid should turn into weak base. So if I started with 0.01 moles of weak acid, at equivalence I will have 0.01 moles of weak base. The question will be, what is the volume at that point? Because remember, what should go in here is a molarity, not a moles. So you're going to have, in this case, it will be 0.01 moles divided by some volume. We're not sure what it is at this point, but make sure you take your moles and divide it by your volume to get molarity before you go through and solve for x in this case. Thanks.